Going to start the show. Welcome back. We're entertaining homework questions. Due Wednesday of next week. How's this going, folks? It's nodding, meaning it's going? Or how nice that you asked. It's only Thursday and I haven't downloaded it yet. It says that's cute that you asked though. Yeah, any one of those. I'm happy to answer questions. I will remind you that they pay me, right? Remember that? I get a paycheck from this place and one of my jobs is to answer your questions. So don't feel like you're burdening me or bothering me. They pay me. I even answer questions from random people from the internet. I have at least 3 of those a week. And do you know why I do that? Because people answered my questions, and that is how I got to be here. And that's what I ask of you. If I answer your questions, you got to pay it forward. You got to answer other people's, and the beat goes on. I know that sounds scary, right? I can see that face. Oh. Eventually, you will feel okay answering questions, and the ones that you can't answer is a great indicator as to what you need to work on. I like questions I can't answer because then I have to go digging and learn something. So they're fun. But these questions, so homework, what is this, 2? Yep, homework 2 over proportional odds and non-proportional odds and nominal models. So, you don't want to ask any questions, Lexi? No?
It was just that.
Just that?
Because I was trying to, yeah.
Mm-hmm. So there's only 2 predictors in this story, right? So as you know, I make up my homeworks based on my life. This is yet another true story from Lisa's life. The Hofflin house has been trying to evaluate where Huey's going to go to kindergarten next year. So I think we've landed on Montessori, actually keeping him where he is. He's very happy about that because he wants to stay in Miss Zanzi's class until he's a grown-up, he tells us. So we're kicking the can down the road in terms of separating them. We're going to stay together for another year, but to be honest, one of the main factors in our decision was the fact that we have after-school care there, and if you go to the public schools, you don't necessarily. So that's a big deal. So you're predicting 2 different types of categorical outcomes from household income, as well as whether or not a family needs after-school care for their kindergartner. And there's 3 sections, and I have instructions here. You will have to download and install GoLogit 2 to do this if you're using Stata. I double-checked, and I am able to install it from inside the virtual desktop without any problems. Those of you who have desktop versions of Stata will be able to do so. And if you're using the research remote desktop thingy, I figured out how to do that. So if you need help with that, let me know. Otherwise, I'm suggesting for your after-school variable, in which 0 is no and 1 is yes, to leave it as it is. Don't treat it as categorical. Leave it as C dot in Stata, or just leave it off the class statement in SAS. That will make your life easier. And for once, there's no interaction terms in this assignment. Can you believe it? I think that's the first homework I've ever made without interaction terms, to be honest. I love them so very much. But trying to figure out what submodel you're predicting is enough complexity, I thought, for this. So no questions? Yes, questions? This. Same. Okay, we've got 2 of those. So multivariate walled tests are available via contrast in SAS or via the test statement in Stata. Stata reports in some of its procedures a likelihood ratio test for the model instead of a walled test. They are going to be asymptotically equivalent, but they will be slightly different numbers in practice. And so this is the version that lends itself most directly to what you learned how to do back in the day in regression. It's the analog to the F-test for the model, the NOVA table in regression. So it should be a test statement and it should be a contrast in SAS. If it's contrast, make sure you have commas separating each of the terms. So it would be like predictor 1, comma, predictor 1 if it's 2 things. In Stata, the analog to that is putting each predictor, setting it equal to 0 in parentheses, where the sets of parentheses denote the numerator degrees of freedom. Excuse me. Okay, does that help at all? You think that's what you used? But it's the wrong number. Okay. Send me an email with the code that you used and the number you think it is, and I will check against the answer key. It's entirely possible I screwed it up somehow, or there's a precision issue in terms of the number of decimal places, but I will check. Okay, did you have a question too? If you used a test statement? Sure. Let's pull up an example, shall we? Let me pull up example 1, part 2, because that's where we did multivariate walled tests for this type of example. Binary DV. Here's part 2. Okay, so here is the first model that's a proportional odds model. It will look the same for the others, mostly the same, I should say. But since that's the question you're asking about, question 2. So in Stata, for instance, this model that we're working with has 3 predictors. Each of them is treated as continuous, and so the test statement sets each of their slopes equal to 0 simultaneously. The analog to that in SAS is this contrast statement right here, where each predictor, I'm asking for one of those, separating the predictors by commas to denote numerator degrees of freedom for the test, and adding the chi-square option so it spits out the chi-square directly as well as the f. Stata doesn't have f's in these routines. It doesn't use denominator degrees of freedom. Okay. Is that what you were looking for, or not yet? A test statement in SAS? Oh, for the non-proportional odds models in proc logistic, it's a different looking statement. Then, so this is the next model that's non-proportional odds. This goes with section 2 in your homework. So this is the test in Stata of proportional odds. So this is whether or not the slope for GPA 3 in submodel predicting greater than 0 is equal to the slope for GPA in the submodel predicting greater than 1. The same thing to test proportional odds in SAS looks like this, where the things after the underscore is what SAS thinks your outcome is called. And so this may just be numbers if you don't have labels attached, such as in this assignment, which I did to try and make it a little bit easier to follow. To test whether all of these things are significant, to do the model test, you would set each of them equal to 0. So you would have 6 terms total in this example because there's 6 slopes total, 3 slopes per submodel. So rather than setting them equal to each other, you'd set each one equal to 0 as the test of whether all 6 things together significantly predict the outcome. SAS would be a contrast statement, yes. Other questions? Okay, well, I'll ask again on Tuesday. Feel free to shoot me emails if you're working on this and you get stuck. Showing me your code as well as what you think the answer is going to be the easiest way that I can check to see if your model is right or where you went wrong or whether I made a mistake, which is always entirely possible. These are brand new homeworks that haven't been tested on anyone but myself, so we will see. Other questions on that? All right. Then I have been working on getting stuff for next week ready. It's not quite done yet. I will let you know when it is done. But in the meantime, we have some count stuff to finish up for this unit. You ready to talk about counts? Yeah. Yeah. I hear it's extra Starbucks day or something. Is that what you're saying earlier? Double star day. Meaning you get twice as much caffeine or you get 2 coffees?
You get 2 copies of happy hour.
2 coffees.
Star days where you get just more stars and points.
Oh, okay, so you're collecting like logits, essentially, to redeem for coffee. Yeah, gotcha. Okay, double star day. I had no idea. So we're predicting counts. That's what we're doing right now. Counts are variables that are discrete. They're integers. The lowest a count can be usually is 0, but they range to positive infinity. To try and have a linear model that can predict the count and keep the predictions within the range of the actual counts, we use our friend loglink. That's almost universal. There are a few others that are possible. I've never actually seen them. So link is log for everything that we're doing. The question is what kind of conditional distribution that we need. So we looked at Poisson, which is sort of the jumping off point. That one is where the mean and the variance are supposed to be the same. It doesn't fit real data very often because of that restriction. So if you want to have more variance than what the model predicts, you need a new model. That gets us into negative binomial, which I call stretchy Poisson. That's where you have this extra factor. It's labeled as a scale factor or as alpha in Stata. It allows the variance to exceed the mean in a quadratic fashion. So the new variance is this right here. You can do a likelihood ratio test, -2 times the difference in log likelihood between the nested models to decide whether or not you keep your K stretchy factor. And you can also examine whether or not the distribution fits sort of in an absolute sense. And that was where we had left off in our example. I had declared victory. Right? Let me find this. Nope, not that one. That's not the one. It was negative binomial. So this thing right here, Pearson chi-square over degrees of freedom. Remember what that thing is? What's it for? Why do I care? Start there. What am I looking at it for?
Not if your model fits your that.
What aspect of the model specifically? Well, models have 3 parts, right? Generalized models in particular have 3 parts. They have what's known as the linear predictor, right? That's the predictors that you put in your model, whether they have fixed effects or main effects, interactions, etc., right? That's the part that you're used to having in every model. But then there's also the link. What are links for? Link transformations. Link functions, excuse me. Link functions, wrong class. What are link functions for? Like log, or logit, or probit, or any of those. Yeah, I'll take gestures. Yep, the walk like the Egyptian, that's the logit curve here. Yep, they take the outcome that has some kind of boundary on it, and they turn it into an outcome that is unbounded that you can then predict with your linear model. So logit solves boundaries both above and below, such as found in categorical data or in next week in terms of proportion correct. Logs solve boundaries below, so things that can't go below 0 like counts. So you have your linear predictor you have to decide about, you have your link function that you have to decide about, and then there's one more thing. What else? What am I missing? Distribution. And conditional distribution, to be specific, because it's the distribution that's left over, so to speak, after your predictors have been taken into account. That's the thing that that number tells us about. And we want this to be 1. Roughly speaking, what that Pearson chi-square value is a ratio of the standard deviation that you find in the residuals relative to what the model says the standard deviation should be. And it's conditional on the mean in a lot of distributions. So like in the Poisson distribution, if your model predicted outcome is 2, your variance is 2. If your model predicted outcome is 4, your variance is 4. And so this thing sort of stretches along with that change so that it's whatever the model says the standard deviation should be at that point. So ideally what the data say and what the model say should match. When that happens, that number is 1. This one is as close to 1 as I've ever seen in real data. So that's why I declared victory. And no, there's not a significance test that I'm aware of to see how close it is to 1. People just sort of look at it and go, eh. Because there's not always a right answer. There's only like what you can do, what's least wrong, really, is where we're going for. So negative binomial up to this point is least wrong because it allows the variance to exceed the mean. It accounts for sort of this extra skewness that you see in count data, such as the counts in this example. So that's one way that we can check whether or not our distribution fits. But the original data, I show you back to the picture that I made, just again, making an eyeball thing here. Here's my distribution. 45% of the observations are zeros. That's pretty high. Given that the mean of this thing is off of 1, you wouldn't expect this many zeros as part of a regular distribution. So the question is, did our model handle them, meaning predict the zeros sufficiently so that after accounting for the model there's not that extra pile of zeros? Or do we still need to do something to fix it? So that's what we get to talk about today. Zero inflated distributions, more specifically, extra zeros. So we're picking up on problems with zeros in Poisson. This is slide 12 in lecture 2. Okay, I mentioned this one because we're going to need it in like 20 minutes, but I don't have an example of it. If you have a count outcome that does not have any zeros, that violates both Poisson and negative binomial. That can happen whenever having at least one count is a necessary prerequisite to being part of the data. So if I get a data set from a hospital and I want to predict the number of days that a patient stayed in the hospital, in order to be in the data set, they have to have been in the hospital at least one day. There will be no zero people, right? Because the hospital wouldn't have them. So you can think about this as instances of, say, extreme behavior or anything else where to get into the study, you have to have this at a minimum of some presence. So, yeah, question?
Again, a random question. So what if you're just centering it?
What if you just center it? Yeah, I tried that. It doesn't work. Yep. No, that's the first thing I thought too, is like, well, I could fix this. -1. Problem solved, right? No, it doesn't work. It doesn't work. The proper way to fix it is to change the distribution. The distributions for these models that do not include zeros, that start at 1, are known as either zero altered or zero truncated. So there is a zero altered Poisson, there is a zero altered negative binomial. Finding these things in software is tricky. They are not very commonly implemented. I had to switch to something I had never actually used before in my life for the next example, but it's showing up here, PROC FMM, which stands for Finite Mixture Model, of all things. It has a truncated Poisson distribution built into it. Stata has these things. There is a routine in Stata called ZTP for zero truncated Poisson, or ZTNB, or TNB, hang on, TNBREG, truncated negative binomial regression. That's how you implement a log link and a zero truncated negative binomial distribution. Stata is better at having like one of these for each combination that you could possibly come across. SAS, you kind of have to hunt for them. It is possible to program these things in NL mixed, and to some extent in M+ as well. But basically what this thing does is take out the expected zeros from the distribution so that what's left, the probability still sums to 1. So it's just a fix where it adjusts for the amount of zeros that should be there, and then it makes the new total out of that. So there's nothing you have to do differently on your end, other than once you pick the right distribution to use it. Now this is going to show up again in like maybe a half hour. 20 minutes was optimistic. Number 3, but what if they have the opposite problem? What if you have too many zeros? This is very, very common. It happens whenever you are mixing together two distinct type of populations and you're asking them how often they do something. So for instance, there's the classic example, I've said this before, how many cigarettes have you smoked this week? People who don't smoke say 0. People who do smoke potentially haven't had one yet, but they have some sort of number. And so when you're mixing together two kinds of populations, then you get these sorts of zero inflated distributions. There are two different ways to handle them. one makes no sense and one makes sense. That's my 2 cents. I'm allowed to have opinions, right? The one that makes no sense is more common because it's programmed into software, but I kind of hate it. So here's a picture to illustrate what these things are going to do before I explain them to you. This is from a real article. This is a count outcome for the number of steps taken towards divorce. I've shown this picture before, but I like it because they did me the solid of overlaying all these different distributions. So if you look at this one right here, the solid gray line, that's where my mouse is, that one right there, that is the fit of a Poisson to this distribution. I don't need my Pearson chi-square statistic to go wah, wah. Right, that doesn't fit, doesn't come close. Here is, let's see, negative binomial is this one right here that's right underneath it. Does a slightly better job, but neither of them account for the fact that there's way more zeros here and way fewer ones, based on what the mean and the variance of these distributions are. So the first fix is to fit an alternative version of each of these things that's known as a zero inflated Poisson or a zero inflated negative binomial. And those are these dots starting inside the zero right here. So if I start from the lower one, that is zero inflated, hang on, where did it go? Yeah, no, right here. Sorry. This right here, start from here. Zero inflated Poisson says, well, I can't predict how many zeros are actually here, so I'm just going to let there be more. I'm going to add a part to my model that says, how many more zeros are there than I thought there was going to be? Okay, I'm going to allow that many. It's like a plug. You just sort of plug the hole. Like you take your bubble gum and you squish it in there and it's problem solved. My distribution fits now. And as however many extra zeros you have, that's how big a bubble gum you need. You just keep, like Hubba Bubba or one of those like big chunky ones for lots and lots of zeros as opposed to like, the tiny little extra ones. But the model just absorbs the extra. And so both the negative binomial and the Poisson, they perfectly fit the number of zeros because they just absorb it into this extra model. It's called the zero model. The rest of the distribution then, after you've factored in the number of extra zeros, is supposed to be Poisson or negative binomial. And you'll see that they kind of map right onto each other. There's not big of a difference. So why do I hate this? Well, there is a nice story that goes with this. And the story goes like this. Oh, well, the extra zeros are structural zeros. Those are the people who would never ever do this, and they are part of a distinct subpopulation. So in this context, it would be, have you taken any steps towards divorce? And some of the people, like myself, in case anyone's listening out there, are so happily married that they would say, are you kidding? I've never even thought of divorce. How dare you ask me that? 0 steps taken. And there's some people that would say, yeah, it's 0 steps taken because I haven't gotten around to it yet. Right? I'm part of the population that's on my way to divorce. I'm just lazy and haven't gotten there. Right? There's 2 kinds of zeros. The indignant 0 and the lazy 0. Same thing with the cigarettes. There's non-smokers and there's smokers, right? If you went into a dorm and said, how many sexual partners have you had this year? There's people who don't sleep with other people and there's people who do, right? This idea of the structural 0 thing, it's so seductive because it makes so much sense intuitively. The problem is at the end of the day, all you know about a person is that they said 0. You don't know why they said 0. And there's nothing that can tell you that because you don't have kinds of zeros in your data set. You only have 0. So the story that goes along with these models is impossible to demonstrate empirically. What you end up with is taking a count outcome and creating 2 submodels to predict it. One of the submodels is predicting the logit of a binary outcome. It is the logit of you being an extra 0. Part of the bubblegum fix So that submodel is predicting whether or not you're an extra zero, and you can have predictors in it, whatever predictors you feel like. It has a Bernoulli distribution because the outcome is binary. Being an extra zero is the 1. Yes, it is backwards. Being a 0 is the 1. See, job security, right? Who does this? Being a 0 is the 1. So you don't have to have predictors, but you can. So it's a 0 model option in SAS GenMod that I'll show you to do this. And the second submodel is your regular count. So it's either Poisson or negative binomial, whatever fits. But here's the trick. It includes zeros in it too. Both models predict zeros. The extra submodel for the extra 0 predicts ostensibly a different kind, but you don't know what kind that is. So if you found a predictor to be significant in one model and not the other, I have no idea how you would talk about that. I think in practice, a lot of people just let the extra zeros be there, like in an empty model. They just let them exist. They don't try to predict them. But the problem in interpretation comes because zeros are part of both submodels simultaneously. And it's trying after the fact to try and carve them up based on what's expected versus unexpected. So have you guys seen these before by any chance in the literature you read? Not yet? No. Are we awake today? Not everybody went to Starbucks, I think. It's Thursday, I know. But you haven't seen these. So it's not too late for an intervention then, to save you. I hate these models. I do. So here is how, if you want to fit these models anyway, you could come up with the mean and the variance put back together again of your count outcome across your submodels. Each case is going to get this thing, which is called omega in the documentation. I stole this from in SAS, I think. And it is the model predicted probability of being an extra 0. Then the mean that you get of the total outcome put back together is the mean of the count part plus 1 minus your probability of being an extra 0. So it's kind of like a weighted mean. Same thing happens with the variance. And the version for negative binomial is slightly more complicated, but it's the same thing. So you are allowed to put these two submodels back together to generate one prediction from them. Okay, so I don't like it. Here's what I like. Let me go back to the picture. Since I don't know what kind of 0 you are, I'm going to put all the zeros together. I'm going to have what is called a series of submodels I have named as if and how much. That's my name. So first submodel, are you a 0? Yes or no? And you can set it up to predict whether or not you're a 0 is the 1 or whether you're not a 0 is the 1. It depends on the software how it does it. But so it'd be like, are you a smoker? Yes or no? Are you a drug dealer? Yes or no? Are you interested in divorce? Yes or no? Okay. Qualitative distinction. Then, how big of a smoker are you if you're a smoker? How big of a drug addict are you? How much do you hate your spouse? Right? If and how much. So the first submodel predicts the logit of being a 0. The second submodel predicts the count among the not zeros. Clean demarcation of if and how much. To do that, these are called hurdle models when the how much part is a count distribution. And this comes from track and field. And if you do high school track, represent? Few people, not only just like 2 of us? Really? I love track, but it's like from the hurdles, you know, you jump over it. It's the same, that's where the word comes from. Because it's like once you've hurdled yourself out of the zeros into the count. I didn't come up with this name. This is what it's called. But you can have a Poisson hurdle or a negative binomial hurdle. And then the distributions that they use is for the binary, are you a 0? That's a logit link with Bernoulli. And then how much, if not zero, is the zero truncated version of Poisson or negative binomial? See, I did get there a lot faster than I thought. Yay for me. And so that way the zeros are out of the distribution. They're over here in the other submodel, and you can predict how much, if not zero. The problem is that it is almost impossible to find these models in software. Particularly once you add random effects, they are really hard to come by. I think there are some user-written routines in Stata that allow these to do them. I've seen them in SAS NL mixed in SAS. It is technically possible to take one of these outcomes and literally split it into the two, have a binary model and run it in a logistic regression setting to predict whether or not you're a zero, and then have a zero truncated count. But the zero truncated distributions are the hard part. Those are not what's built into things. So even though I like this model conceptually, it's difficult to fit in practice unless you're willing to write custom routines in your software packages, or of course, do it in Bayes via JAGs. I have to say that. That way I don't get divorced. So that being said, I have demonstration for you on how to fit at least the zero inflated ones, and I'm saving the if and how much for when we get to multivariate options. But here is my laundry list of where you can find all of these choices in SAS. There's different procs that have different combinations of these things. They overlap to some extent, but not entirely. And then here's the list that I found for Stata, all of these different things. The thing that I couldn't remember the name of, it's MENL. That's the analog to NL mixed where you can write your own model. So you can define your own model and your own link and log likelihood function so that you can do anything that's not already programmed. So do you want to see it? So I didn't do the hurdle versions yet for you, but they're coming. I did the zero inflated versions because that way you can test whether or not a zero model makes any kind of sense. So in this situation, this is an experimental study where people are being manipulated and they're measuring their outcome. It's harder for me to conceptualize like what being a zero means differently from being rest of the distribution. It's not like there's mean people and not mean people, the way there's smokers and not smokers. I have a harder time thinking of this as two subpopulations. But it is still true that we may have more zeros than is predicted by the model, and we have to address that somehow if that's the case. So let's find out if that is indeed the case. So I am going to, towards the end, but not quite, I think we have 3 models to go. Here it is. This is page, I don't know, 11? Yep, bottom of page 11, that's where I'm at. This is example 2. So same data, same story. We are predicting number of mean things said from a covariate of whether or not they said anything mean in the neutral condition, and then main effects and an interaction of history of IPV, yes or no, and then assignment to one of 3 strategy conditions, none, cognitive reappraisal, or suppression. So to do this in Stata first, there are 2 changes relative to what we've seen before. First off, ZIP, zero inflated Poisson, that's what I'm fitting. The other thing that's new is after the comma here as an option is this thing, inflate. That is asking you what do you want in the model that predicts whether or not you're an extra zero. And what you want in the model goes in parentheses. The fact that I have underscore const, what's that thing? That's the intercept, meaning with respect to predicting whether or not someone's an extra zero, I am fitting an empty model for that submodel, no predictors. I'm just asking whether or not there are extra zeros in the first place. I am predicting the expected zeros and the rest of the outcomes with the same linear model I've been using this whole time, as just described. There's also an option on here for the link I just found this morning, actually. The link of the inflation model, confusingly, it's iLink. iLink doesn't mean inverse link, it means the inflation model link. Job security. So that apparently is a default, but if you wanted to change it, that's how you would do so. Like I said, I literally just learned that this morning. In SAS, I'm using proc genmod. Generalized modeling, I think is what that stands for. So I have the model part that looks like normal. Instead of log and Poisson, distribution equals 0 inflated Poisson. The extra part that you haven't seen yet in SAS is right here, 0 model. That's where you would write out the predictors that predict whether or not someone's an extra 0. And there's no predictors there, meaning that it's just fitting an empty model. So it gives you an intercept by default, you don't have to say it. And the link for that 0 model is logit. So there's two things going on here. I am trying to predict whether or not you're an extra 0 with a logit link in a Bernoulli distribution. So that part's a logistic regression. That's the 0 model or the inflate model. Then I'm predicting the count of number of mean things said, including zeros expected by the count distribution from the rest of my predictors. How are we doing? Do you see why I hate this? Like, we haven't even gotten to the results yet, and I'm exhausted from explaining this. So these models are trying to fit distribution misfit from a different perspective. Whereas we had a count and that was Poisson, and we added negative binomial that has a stretchy factor that allows more variance. Another way to try and fix it is to add more zeros. That way it doesn't necessarily need more variance. So it's an open question whether we need extra zeros, just a stretchy factor, one or the other or both. So I'm going to fit both versions of the zero inflated models, the Poisson and the negative binomial, and see if they're better than what we have so far. So the output from GenMod looks a little bit different, but I've highlighted the things that we'll pay attention to in terms of absolute distribution fit. This line right here, that's our friend Pearson chi-square over degrees of freedom. That value is 2. Do you remember what mine was from before? It was 1.1. Yeah, so 2 is bigger than 1, which means what? It's worse. Yeah, feel free to read. I'm shameless at getting audience participation. I will give you the answer just so we can all pretend like we're participating. I also looked at the AIC and the BIC. These are metrics in which smaller is better, although the absolute value of the numbers are meaningless. They're tied to the scale of the outcome. These are higher, they're worse than for the previous model. So far it looks like switching from negative binomial back to Poisson is a problem. Even if you allow extra zeros, it's not as good. So Poisson's Pearson chi-square was around 4. This one's 2, which is still better, but the negative binomial of 1 is still so far our best bet. So the part that we care about is what happened with the 0 model. So this intercept right here, so the 0 inflation parameter estimates, that estimate right here, this minus 0.55, that is the logit of being an extra 0, assuming the rest of the distribution is adequately modeled by Poisson. So that's kind of a big number. How big is it? Do you remember how to find out? How do I unlogit a logit back into probability? Think about it. As soon as Excel decides it's ready, I'll ask you again. How do I unlogit, otherwise known as inverse link, a logit down into probabilities? So the number This is in logits. How do I get it into probability? Anyone remember? E to the logit. Excuse me. Yeah. Here, I'll write out the formula first. Come on. E to the logit over parenthesis, order of operations here, 1 plus e to the logit. So if I do that, equals e to the that thing over parenthesis 1 plus e to the that thing, double parenthesis, 0.36. So the model says I have like a 37% chance of being an extra zero. That's definitely not zero. Like, it looks like there's some tendency for people to be extra relative to the distribution. Is extra a compliment nowadays? I'm just checking, because like I see signs like advertising stuff like feeling a little extra today, like buy this extra thing. Is extra a good thing? Maybe. It depends. The context. So when would it be a bad thing? When you're doing too much. So if I have like 12 necklaces on, that's extra.
Oh yeah.
Okay, good to know. I'm counting on you guys to keep me young, right? Keeping up with the kids and their jargon. Huey is too young to make fun of me for being old yet. Although I do have a funny story to tell you. My husband was getting off an airplane recently, and he had a toy car he had bought for Huey. And the pilot said to him, "Oh, someone's grandson's going to be happy to get that." That was his response. Yes. Yeah. Unlike me, his hair doesn't magically reverse the aging process every 4 to 5 weeks. I refuse to surrender and be called grandma. I just refuse. But he's accepted it. I haven't. But anyway, 37% extra. So that could be bad in this context, but we're not trusting it yet because the model doesn't fit. So how do I make it better? ZINB. So now I have a zero inflation and a negative binomial. And foreshadowing what's going to happen, note that I have this all in comments here because Stata blew up. It was just like, nope, I'm going to run for like 10 minutes and not give you anything. Could not complete optimization or something like that, right? It's like, nope, I have no idea what this model is supposed to be. You figure it out. And I get this note from SAS in the output. Algorithm converged. Well, that sounds helpful. This is my note for you. Wait for it. So we'll play Where's Waldo. And I want you to spot something on this screen that might cause you to be suspicious about this model output. Scaled Pearson chi-square is 1.14, a little higher, but not bad. AIC and BIC. Let's zero in on here. The standard error is 39,000. That is a lot of logits. Yeah. So this is one thing to be watchful for in practice with these models. You can get no error messages whatsoever. It will say convergence reached, criterions good, go ahead, and then you get this. And it's like, what the hell am I supposed to do with that? And note that it gives me confidence intervals. The logit of being an extra zero is somewhere between negative 77,000 and positive 77,000. Well, that's helpful. That's the entire number line. So yeah, this means, this is SAS's way of telling you what? You
messed up. I like that.
You messed up. It's like, okay, well, you asked for this and I'm going to give it to you, but I have no idea what the crap this is. Like, I can't find it. But the rest of the model was solved to enough precision that it ejected from the algorithm to go find better versions. It can't find it. So yeah, the logit of being an extra zero in this model, which fits otherwise reasonably well, is a logit of negative 22. a logit of negative 22. Oh, wait, I already did it for you. I was going to do it in Excel. This is the probability of being an extra zero. So in other words, we don't have any extra zeros. And when you asked it to find some, it can't. So that is a good indicator that we don't need extra zeros. So I am saved from the extra work and complication of having to fit some sort of zero inflated model or hurdle variant, because for all evidence, it looks like after putting in the predictors, we know why the zero values are there. They're not unpredicted, they're not extra. They are part of what the model has accounted for. Okay. How are we doing? Eh? So this if and how much thing, this is coming back in the next unit too, because these types of hurdle models can be applied to other types of continuous distributions. Like if you have, I have an example where there's response time. This is from my dissertation, and they had up to 45 seconds to complete some task. And if they didn't get it within 45 seconds, I shut it off and I called it wrong. That's a hurdle model, because I could predict, okay, did you do it? Could you do it at all? Could you do it within 45 seconds? Yes or no? That's one set of prediction. Then if you could do it, how quickly could you do it? There is an example from my job talk for this university based on a paper, someone else's master's thesis that actually got published. They're so rare. It was for a task called the stoplight task. Any of you study adolescent development by chance? No? Okay, well, then I'm the expert in the room. All right, today I'm a developmental psychologist. It's a task where you're told that you have to get to a party as fast as possible. It's a computerized task. And you're driving a car, and you have a series of stoplights. No? No? Keep going. Okay. And the stoplights turn yellow, and you can decide that you can race through it or you can stop. But if you get in a wreck because you ran a red light, you're going to be late to the party. It's bad. So it's supposed to measure like risk-taking or impulsive behavior or whatever Reviewer 3 wants us to call it that week, right? Tendency to be reckless. And traditionally in this task, they measure response time to hit the brake. And they take the mean response time to hit the brake across trials, and that's your score, where hitting the brakes sooner is less reckless behavior. Well, that begs the question, what if you don't hit the brake? What if you floor it? Do you think that is indicative of reckless behavior? Is that data really missing? Not really. I mean, it's the definition of missing not at random, right? They don't have a response time because they floored it. So I was talking about these models in a generalized class, and a person raised his hand whose master's thesis this was, and he's like, could I do this hurdle thing for that data? I said, hell yes, you can. And it worked out that we actually fit a latent variable measurement model that did a hurdle version of this. So we had a latent factor for one's tendency to hit the brake and a latent factor for how quickly they hit the brake if they did. And it worked out that the tendency to hit the brake, the part that they typically treated as missing data in this task, was the only thing that predicted the outcomes he was interested in. It was cool. I liked it. It's one of my favorite examples of taking models that other people haven't heard of and bringing them to something else to solve problems. So in that case, it's not a traditional hurdle, because the response time distribution has to be something continuous. It's not a count. But it has the same characteristic in that it has to be above zero. So we have gamma and log normal distributions that we can throw at that, but it's the same idea. Those models tend to be called two-part models if the count part is actually continuous instead. But so that's coming next week. But in the interest of continually expanding my horizons and yours, I learned something new to put this together. I want to show you guys one more model because I thought it was cool. A heterogeneous negative binomial. Some genius has already programmed this into Stata, and I asked the Google for the SAS equivalent, and I came across a handout by this person who's at the University of Nebraska Medical Center. So thank you, Robin, for your efforts that I stole and put in this handout. The idea is, rather than just having the stretchy factor be there, like variance exceeds the mean, so we're just going to put in a stretchy to let that happen. That you can phrase the model as asking whether different people need different stretchies. Are some people more different from each other than other people? So it's this idea of non-constant variance, but it's turning it into something interesting. Inconsistency or individual differences. So the addition to the model is right here. So rather than having an inflate submodel, this is a submodel that takes that k stretchy factor and predicts the log of a k from a different linear model. I threw in the same predictors that we had except for neutral. Actually, I did throw in neutral. I need to adjust this. Hang on. I had a couple different versions of this that I was playing with. Neutral should go in there. Put that there. I'll fix this after class and repost it. And so then the output has two sections to it. Here's the original negative binomial model. So it's predicting the log of the count of mean things said, same as we had talked about last time. And here's the new part. Ln alpha. Alpha is Stata's version of k stretchy. It predicts the log of it so that it can't go negative, because you can't have variance less than 0. But this is asking whether or not different people need different k factors as a function of these covariates. So for instance, the effective neutral is negative. So people who said something mean during the neutral condition are less variable than people who didn't. So rather than predicting the number of mean things said, it's the variability of mean things said that this is a proxy for. People who have a history of IPV are less variable when they're in the reference condition, but not significantly. So here's the p-value column. You can scroll through these and see that they're all non-significant. And you can see this. Standard error of 45 in predicting a logit, not good. So a sign that the model has too much stuff in it if it can't figure out what all the parameters should be. So in terms of whether adding this stuff helps the model, the answer is no. I can do a likelihood ratio test to see if adding these things helped. It doesn't, but I wanted to show it to you because I thought it was cool. And then here's how you do it in NL mixed. Writing out the model. So I have my linear predictor here, and I have betas that go with all of the fixed effects in predicting log count. I have my scale model here, and I use D's for dispersion for all the fixed effects of that. And then here's the log likelihood function, and this is the part that, thank God, this person figured this out so I didn't have to, because that is not where I'm good at. And then there's the model statement. So NL mixed is a way that if you ever come across something that isn't in SAS, you can put it in SAS. And if it's a model that's been published, people have probably tried to do this. The Stata analog to this was like MENL or something like that. And I was happy when I got the same answers back as I got out of Stata with the same potential problems of estimation. So SAS thinks the standard error is 339 rather than 49, but it's still indicative of a problem. So that means we probably don't need all this extra stuff predicting the dispersion factor. But again, I thought it was cool. And as usual, words. So the order of this results section is different than the order in which these models are presented. When you write a results section, you do not want to bore your reader with every rabbit hole you went down finding your final model, right? This process of finding your final model is right here. So this is my reporting of checking distribution fit, deciding when adding a different distribution made the model better, reporting -2 log likelihood differences whenever possible to see if adding something to the model, such as a stretchy dispersion factor going from negative binomial from Poisson, and then checking for zero inflation, checking for heterogeneity of the scale factor, and then you get down to the story. So 3-paragraph structure. This first paragraph right here, how we did what we did, what software did you use, how did you parameterize the model, how are you giving effect sizes, all that kind of stuff. Sometimes people want you to put this in the method section. There's the last paragraph of the method section, and certain journals want you to have something called analytic method, and that would go here. I personally hate that, because then it's like you tell them how you're going to do what you're going to do, and then like 5 pages go by, and then the results show up. So I find that inconvenient to have them separated, but you have to pay attention to the format that your journal wants. So this is like how I did what I did, how I know my model is the rightest one, or least wrong, really, and then what happened. And so this part then is detailing the simple effects and the simple effect differences that were supporting the interaction term. And then you'd make a picture and you'd have a table and you'd write it up and turn it in. All right, questions? Feel like you could do this in an assignment? Maybe not this last one, but like counts? You want to practice some counts in the next one? Maybe? Yeah, that's not so bad. It's log count. So most of it's pretty straightforward in terms of the linear models aspect is not different. Trying to figure out what software package to use and what distribution goes with it is the trickier part for these. So I promised you that any time left you could work on your homework. That promise still holds, so you have about 15 minutes. So I will adjourn from lecturing here and ask if anyone needs help. Office hours essentially start now then. So if you don't need help, then I shall see you next week. Let me know if you need anything in the meantime.